Hello everyone and welcome to part 2 of the course. In this part we are going to discuss the subject of the staircase pressurization systems. Staircase pressurization systems are very complicated and we are going to simplify it and cover it in great detail. Our basis of discussion will be built from NFPA 92 and International Building Code. So this part of the course is divided into three main topics. The first topic, which is the staircase pressurization. The second main topic, which is a brief introduction on the zoned smoke control systems in high-rise building. And the third topic, which is the example or the solved example on the staircase pressurization calculation and design. So with regards to the first subject, which is the staircase pressurization, we're going to start by defining the basic questions, which are what is the staircase pressurization and why using the staircase pressurization and how do we use the staircase pressurization. After this, we are going to discuss and clarify the system components and types of the staircase pressurization. After this, we are going to discuss the pressure limitations, because this is from the name a staircase pressurization, so there has to be a limits, and this is what we're going to cover on this section. And lastly, we're going to talk about the open and the closed door leakage and how to define the leakage and how to calculate and specify the leakage and the related pressurization. So without further ado, let's dive right into it. Let us start by asking the basic questions. What is the staircase pressurization? Why and how is the staircase pressurization is applied? First of all, in the majority of the buildings, especially the mid-rise and the high-rise, the stairs are typically the most important means of egress during a fire scenario. That's why it is very important that these stairs, especially the exit stairs, to be completely free of smoke and to incorporate a design feature that improves the speed of the occupant during the evacuation. That's why most building codes require the exit staircase to be pressurized to keep the smoke out of these egress paths. In other words, the staircase pressurization prevents the migration of smoke into the staircase pressurization area or the area usually used for egress or as a refugee area. Also, staircase pressurization maintain a tenable environment in the exit path of the occupants while they are trying to escaping from a fire on the staircase, which means that it helps to protect life and reduce any casualties or loss in life. Because if a smoke infiltrated into the staircase, then the majority of the people in the staircase will suffocate from the smoke, because there is no vertical obstruction that prevents the smoke from traveling anywhere inside the staircase shaft. That's why it is very important to maintain the staircase, especially the exit staircase, free of smoke during the normal operations of the building and during the fire scenario or the emergency scenario. So how does the staircase pressurization system work? Simply, it injects or pumps or supply air into the staircase pressurization in order to positively pressurize the enclosure of the staircase. And this means that as a result, the airflow is going to flow outward from the staircase into the cracks and into the open or closed doors. And this will achieve the purpose of the staircase pressurization system design, which is that no smoke should enter the stair in the event of a fire or in normal operation mode, which will mean ultimately a safe evacuation environment for the occupant of the building. Okay, but now we have clarified what is the staircase pressurization and how it works. Now we need to understand what are the limitations that surrounds the design of the staircase pressurization. The first limitation, which is the minimum pressure difference. Minimum pressure difference, in some cases, it may not be enough to prevent the smoke infiltration. And secondly, the maximum pressure difference. Maximum pressure difference may be causing an excessive forces on the cracks and on the doors of the staircase. And lastly, the height limit of the building and the stack effect and the buoyancy effect and the other factors that affect the smoke movement, which is explained in part 1 of the course. Okay, let's try to simplify it further. By the minimum pressure difference, I mean that as a concept for the staircase pressurization, you try to pump air inside the staircase so that it have a positive pressure. This positive pressure will mean that the air will come the air will flow from the gaps of the staircase, and in case if you open a door, it will still flow from the staircase outward, not the opposite, which means that you as a designer will choose a value or a limit of pressurization or a certain pressurization value that you will try to employ a system that will apply it and maintain it in the staircase pressurization enclosure. Okay, but what if this pressure difference is relatively low? This will mean that the limitations will be exceeded very easily. Like for example, if you have a pressurized or a positively pressurized staircase, and if you open more than one door, what will happen? You will lose the pressurization value if you chose a very small pressurization value. What will happen also if you choose a very small pressurization value? This means that in some cases, the amount of air flowing from the cracks in the walls and from the gap below and above the door may lead to equalization of the pressure difference if the pressure difference value you choose is very low or low. Also, in the event of an evacuation, if the occupants open the discharge door, which is located at the ground floor, which is discharging from the building into the street, you will also suffer from a pressure loss. That's why it's very important to try to choose a pressurization value that is not the minimum value. Try to choose a value which is in the middle between the minimum and the maximum to account for the actual operating conditions like opening doors and the infiltration from gaps and all of this. Additionally, you may suffer a loss of pressure because of the external factors that are affecting the airflow and the smoke movement within the building. Like for example, the buoyancy and the stack effect, like we explained them in part 1 of the course. Okay, so what about the maximum pressure difference? Well, maximum pressure difference exerts too much force on the doors, which you are, as an occupant, will need to open to enter the staircase. And of course, as we all know, the evacuation doors always open in the direction you need to escape to. So for example, if I am a person which is inside the corridor and I try to open the staircase door to enter the staircase to later escape through the staircase back to the street, if the pressurization value is too much, you will find a resistance from the pressurization while you are trying to open the door. If it's excessive pressurization, in some cases you will not be able to open the door because the pressurization inside the staircase is too much, and this can be a problem for people who are relatively young or of old age. And we are going to cover this on the pressure limitation section of this part of the course. So whenever the subject of staircase pressurization is opened, you will find yourself talking about the orifice equation. Orifice equation is the main equation used in the staircase pressurization, and it allows you to estimate the amount of flow which you need to supply into a certain space, or in our case into the staircase, in order to maintain a pressure difference of a specified value. So to give you a simpler definition of the orifice equation, the staircase pressurization is similar to blowing air into a balloon. The balloon in our case is the staircase, and the air you are blowing from your mouth is represented by the supply fan that is supplying air into the staircase. So you will notice that if you grab a balloon and start to blow air into the balloon, you will increase the pressure inside the balloon, so it will expand and the volume will increase. The same case applies in the staircase. If you supply air into the staircase, because it's normally closed space, you will increase the pressure relatively inside the staircase enclosure. However, if you go back again to the balloon example, if you started to make gaps in the balloon, what will happen? The air will escape from these gaps outside from the balloon. And if you started to increase the number of holes or gaps in the balloon, you will notice that the amount of air escaping from the balloon will increase and up until you reach to a point where you ultimately, no matter how hard you blow the air into the balloon, it will still contain or maintain the same pressure or the same volume. It will not increase in pressure and it will not increase in the volume. And in some cases, the amount of air escaping from the balloon will be more than the amount of air you are blowing from your mouth into the balloon. And the holes or gaps in the balloon are represented in the staircase by three things. The first thing, which is the gaps around the frame of the doors of the staircase. As we all know, any door have a certain amount of gaps. Of course, these gaps are expressed in millimeter. They are relatively very small, but still they are still a gap. So this gap will lead to the air pressurizing the staircase to escape from it outside to the corridor or to other areas that are joining to the staircase. This means that you need to account for the number of gaps or holes or cracks around the door frames in your staircase pressurization system. And because we can estimate the amount of area of these gaps, we can identify that this is the flow that I need at a certain amount of pressure difference. And secondly, the biggest problem in the staircase pressurization, or the biggest cause of the loss of pressurization, which is if someone opened the door. If someone opened the door, this will lead to a relatively large loss of pressurization through the area of the entire opened door. So instead of air being exfiltrated from the gaps of the closed door around the frame, no, it will be exfiltrated from the entire area of the open door. And the third component for the leakage, which is the cracks in the concrete itself. These cracks can be at the joining points of the concrete wall and concrete slab, or it can be in numerous spaces. It depends on the construction process, how it was done, and so on. So in these three scenarios, you can identify how much flow you need in order to maintain a pressurization level that is predetermined by using the orifice equation. And the orifice equation, if you can see it on the left side of the screen, you can see that Q, which represents the infiltration flow in CFM, equals 2610 multiplied by the area of the leakage multiplied by the square root of the pressure difference, which, if we try to translate it into simpler terms, this equation will mean that if I, as a designer, wanted to maintain a specified amount of pressurization, and if I have the area of the leakage, then I can easily obtain the pressurization CFM that I need to supply into the place. And this equation is obtained from ASHRAE Handbook HVAC Applications, the version of 2011. And if we refer to the figure on the left side of the screen, we can see that this is a simplified figure that you can find on it the room differential airflow required versus the differential pressure. You can use this curve as a simplification instead of doing the calculation using the orifice equation. You can see that this figure have two axes, the horizontal and the vertical. Horizontal axes represent the pressure difference in inches of water gauge, and the vertical axes have the room airflow required in order to maintain this pressure. And you will see some curves which are tilted on this figure. These curves are representing the leakage area. So for example, if the leakage area of my door is 1.5 square feet, then I will go to the curve on the top on this figure. So let's say, for example, if I needed to maintain a pressurization value of 0.001 inch water gauge, and I will enter this figure by going to the horizontal axis and I will look for the value of 0.001, which is the first value from the left, and then I will go vertically upward until I hit or intersect with the curve of the 1.5 square feet. Then I will travel horizontally distance until I hit the airflow axis, which is a vertical axis. So if I want to maintain a pressurization of 0.001, I will go vertically upward and I will intersect with the curve of 1.5, and then I will travel on the horizontal axis. This will give me a flow of approximately 125 CFM. So 125 CFM of supply air will maintain a pressurization value of 0.25 Pascal. Let us discuss the staircase pressurization system components. Staircase pressurization system mainly consists of four main components. The first component, which is the pressurization fan, and the second component, which is the pressurized air distribution network, which is the ducting and the grills, and the third component, which is the related life safety dampers, and the fourth and last component, which is the controls. The first component, which is the pressurization fan. Pressurization fan is required in order to supply air into the staircase, and this is done usually by adding a fan that is connected to a distribution network, and usually this fan is located on the roof among the rest of the mechanical equipment. And it's also located on the roof to keep it from tampering with it, and to keep it from sucking air that is at low level, which is probably having pollutants from the roads. This fan is responsible for supplying air constantly into the staircase enclosure to maintain it under a positive pressure. The second component, which is the pressurized air distribution network. This pressurized network is usually defined by two main major components: duct and grill or air outlet. The pressurization duct is a series of ducting extended from the roof where the fan is connected vertically downward on a shaft that is usually adjacent to the staircase enclosure. And the second component, which is the grills or the air outlet, and these are usually wall mounted at a predefined interval, and as a rule of thumb it is distributed every 3 floors as an average. And component number 3, which is the dampers, and as we know, the enclosure of the staircase is a smoke-proof and fire-proof enclosure, which means that whenever you are penetrating this enclosure, you need to install a life safety damper. If you are infiltrating or penetrating a smoke-proof enclosure, then you will need to put a smoke damper. If you are penetrating a fire-rated enclosure, then you need to put a fire damper. If you are penetrating a fire and smoke rated penetration, then you need to install motorized smoke fire damper. This is mentioned in International Building Code and in the majority of local civil defense regulations, and we will discuss it under part 6, which is discussing the life safety dampers. Additionally, you need to install a means of disposing or getting rid of the excessive pressure accumulation inside the staircase. That's why you need to install a pressure relief damper. The pressure relief damper can be installed at high level or at wall mounted levels. And lastly, the controls and the sensors that are sensing the level of the pressurization and giving back a signal to the fan to operate and activate or deactivate. In this video, we're going to discuss the staircase pressurization system types. Staircase pressurization system have 4 common design methodologies or 4 design strategies. Any designer can use at least one of them, if not more. And these staircase pressurization system types can be seen on the figure on the right side of the screen. The first design strategy, which is the single injection, and the second design type, which is the multiple injection. The third staircase pressurization system type, which is the compensated system, and the last one and the fourth one, which is the non-compensated system. Let us start our discussion by the single injection point. The single injection point or the single injection staircase pressurization system is having the advantage of being one of the simplest systems ever used, but it's also having one of the major weaknesses that are available. By single injection, it simply means that you will use only a single injection point to pressurize the staircase, which means that you will use only one fan, and the fan will be either wall mounted or roof mounted. Wall mounted can be wall mounted on any wall at any location or any elevation, and roof mounted, it will be mounted on the roof slab of the staircase. This is very simple because it's very cost effective. There is no need for any duct, and there is nothing is required except for putting the fan on the wall or the roof. However, the designer should consider adding a wind protection mechanism in order to protect the fan from direct exposure to the wind if it is put in the direction of the wind blowing direction to the building. And one of the most common places to put the fan in this single injection scenario is to put the fan either on the roof or at the ground floor. On the roof, it will have the advantage of being located and situated among the mechanical equipment, so it will be easily maintained and protected from tampering with or messing around. However, if you put it on the ground floor, you can suffer a sudden pressure loss if the fan is located near to the exit exterior door. And it is expected during an evacuation that the exterior door will be open, which means that in this case you will suffer from a short circuit between the fan and the door. That's why you will suffer from a pressurization loss inside the staircase, and this is one of the major weaknesses of this system. Okay, but what about the other installation limitations? The installation limitations in this single injection system is mainly the pressure failure. Pressure failure can happen easily when you open few doors that are located next to the fan, which means that if the fan is located at the roof and you open a few doors from the top floors, you will suffer from a pressurization loss because the air will short circuit from the fan and will exit from these open doors. And also, if you put the fan at the ground floor near the exterior door, then if you open few doors near to the fan, you will suffer from the same consequence. And also, if you put the fan on the walls in the middle of the staircase, and in the case of opening few doors at the middle floors, you will suffer from the same result. Also, the second largest limitation of this application for this system is the maximum applicable height. Maximum applicable height for this system is set and clarified by ASHRAE to be on the range of 8 up to 12 floors, and it is highly recommended to maintain the maximum applicable height only to 8 floors. This will provide you a partial protection against the undesirable other limitations. And the last limitation, which is that it is highly recommended that supply inlets or supply fans or supply injection point to be at least 1 floor above or below the exterior door, because the exterior door is the most opened door during any evacuation, and trying to allocate the fan as far as possible from the exterior door will provide partial protection against any pressurization loss. Following to the single injection is the multiple injection. Multiple injection system is usually built with the supply air injection points that are distributed evenly each floor or each few floors. The multiple injection also have the main advantage that overcomes the major weakness in the single injection, which is the pressurization loss in case of few doors being open. So the main idea behind the multiple injection is to provide injection points at each floor or at a fixed interval each few floors, and this will in turn maintain the pressurization value if a few number of doors was open. It will provide a proper distribution of the pressurization air throughout the entire vertical section of the staircase. You need also to know that the duct is usually located inside the shaft that is adjacent to the staircase. However, it can be inside or outside the staircase. It is highly recommended also to maintain the injection points at 3 floors apart, which means that if you have a building consisting of 9 floors, you will have 3 injection points. If you have a building consisting of 15 floors, you will have 5 injection points, and this is recommended in accordance with ASHRAE requirement. As we can see on the figure on the right side of the screen, we can put the fan on the roof or at low level near or at the ground floor. Of course, each one of them has its advantages and disadvantages. For simplification, it is highly recommended to maintain the mechanical equipment on the roof, because they will be easily accessible for maintenance, and they will be also protected against any sabotage or any messing around. However, if you put the fan at the ground floor, it will have the main disadvantage of being at the road level, and this road level is usually having a high percentage of dust, and this is not desirable because it might affect the fan performance and it might pump dusty air inside the staircase. And this problem is solved if you put the fan on the roof, because the air at the high level of the building is usually cleaner than the air at the lowest level. Now let us discuss the compensated versus the non-compensated staircase pressurization systems. Let us start by the non-compensated. Non-compensated pressurization system is usually done or achieved by maintaining a positive pressure by using a single speed fan. This is the simplest, and it provides one pressure difference with all doors closed. It also provides one pressure difference with one door open. This means that you will pump air constantly with a constant value using a constant speed fan inside the staircase. You will not variate anything inside it. But the compensated system maintains positive pressure while providing the availability to adjust the flow to a various combination when various doors are open or closed. And this gives you a modularity option, or it is similar to using a VFD on the fan. And instead of using single speed fan, you put a VFD. This will provide you the option of varying the flow to respond to more dynamic loads of door opening and more dynamic pressurization values. You need also to know that the compensated system utilizes a pressure relief mechanism in order to get rid of the excess pressure that is accumulated inside the staircase. However, the non-compensated does not use that. And this flexible option provides you more flexibility to adjust the pressurization value inside the staircase, more than using a single speed fan for a non-compensated system. So in short, the compensated system is named compensated because it compensates the pressure difference and the pressure variations using a adjustable fan and using a means to get rid of or relieve the excess pressure accumulated inside the staircase. but the non-compensated is non-compensated because it does not compensate any of these items. So the compensated system can be done by two main strategies or two mechanisms. The first one, which is to modulate the airflow, and the second one, which is the overpressure relief concept. In this concept you use a pressure relief damper. Let's discuss first the modulating of airflow option. In this option, the supply fan will be sized normally to provide the minimum velocity and pressurization value or pressure difference when some doors are open and when some doors are closed, as the usual sizing process. However, the flow rate into the staircase will be varied by using one of the following options: modulating bypass damper, VFD, inlet vanes, or any of these options that are normally used to vary the airflow around a fan. And we can see on the figure on the right side of the screen the modulating bypass with the bypass damper around the fan. Also in this option, the airflow is controlled via a static pressure sensor. The designer also needs to evaluate the response time of the controls and the sensor in order to avoid any pressure loss scenario in case of sudden pressure change inside the staircase. So the compensated system can be done by two main strategies or two mechanisms. The first one, which is to modulate the airflow, and the second one, which is the overpressure relief concept. In this concept you use a pressure relief damper. Let's discuss first the modulating of airflow option. In this option, the supply fan will be sized normally to provide the minimum velocity and pressurization value or pressure difference when some doors are open and when some doors are closed, as the usual sizing process. However, the flow rate into the staircase will be varied by using one of the following options: modulating bypass damper, VFD, inlet vanes, or any of these options that are normally used to vary the airflow around a fan. And we can see on the figure on the right side of the screen the modulating bypass with the bypass damper around the fan. Also in this option, the airflow is controlled via a static pressure sensor. The designer also needs to evaluate the response time of the controls and the sensor in order to avoid any pressure loss scenario in case of sudden pressure change inside the staircase. However, the second strategy to achieve the compensated pressurization system is to use the overpressure relief concept. Overpressure relief can be accomplished by one of the following methods. The first method, which is to use a parametric damper with adjustable counter blades. It's similar to the gravity damper or the backdraft damper, but with adjustable weights that you adjust according to the amount of pressure difference which you need the damper to open at to relieve the excess pressure. And the second option, which is to use a motor operated damper, and this is usually more accurate. The third option, which is to use an automatic opening stairwell door or vent at the ground floor level. In this case, instead of depending on a damper, you will depend on the door, the exterior door, to open for a specified amount of time to relieve the excess pressure and then to close again. And this is all motorized. The fourth option, which is to use exhaust fan that can be mounted on the stair enclosure, and it can be used when all the stair doors are closed to avoid any pressure accumulation that will exceed the acceptable limits to prevent any extreme opening forces on the door. It is very important to understand and avoid the pressure limitations when it comes to the staircase pressurization. It's also important to try to use a value for the pressurization which is a little bit higher than the minimum value to avoid any pressurization loss in case of any doors opened, and to also avoid using the maximum pressurization value, because if any slight accumulation of pressure happened, you will exceed it, and then you will pose a very difficulty on the people to open the doors leading into the staircase. If we refer to section 4.4.2.1, which is shown on the left side of the screen and quoted from NFPA 92, and this section is titled as the pressure difference across spaces. You will find it saying that table 4.4.2.1.1 shall be used for design that are based on maintaining the minimum pressure difference between specified spaces. And it's also saying that where the system designer has determined that a higher minimum pressure difference is necessary to achieve the smoke control system objectives, the higher minimum pressure difference shall be used, which means that you doesn't necessarily use the minimum pressure limit. you can use and specify a value that is higher than the minimum. And lastly, it is saying that the minimum pressure difference for the smoke control system shall be established at a level that is high enough that it will not be overcome by the forces of wind or stack effect or buoyancy effect of hot smoke. And if we refer to the right side of the screen, we can see table 4.4.2.1.1, which is titled as the minimum design pressure difference across the smoke barrier. This table consists of three main columns. The first column, which is the building type, the second column, which is the ceiling height, the third and last column, which is the design pressure difference in inch water gauge. The first column, you will find it mentioned AS or NS. AS refers to automatic sprinklers, while NS refers to non-sprinklered. And the second column is the building height. The third column is giving you the pressure difference, the minimum pressure difference limit that you should not go below. So if we refer to row number 1, which is in the building type AS and in the ceiling height of any, you can use the minimum design pressure difference of 0.05. However, if the building is not sprinklered, then you will notice that the pressure difference will increase along with increase of the building ceiling height. You will find it in the building ceiling height of 9 feet reaches a value of 0.1. However, in the building ceiling height of 21 feet, the value will increase to 0.18. And if we refer to the notes below the table, you will notice that AS means sprinklered and NS means non-sprinklered. And there are some notes also. Note number 1 is saying that this table presents the minimum design pressure difference developed for a gas temperature of 1700 Fahrenheit or 927 Celsius for the smoke. And note number 2 is stating that for design purposes, a smoke control system must maintain this pressurization or minimum pressurization difference under specified design conditions of stack and wind effect. The last note is saying that for zoned smoke control system, the pressure difference is required to be measured between the smoke zone and the adjacent space while the affected area are within the smoke control mode. When it comes to the maximum pressure that needs to be followed and not exceeded, we will refer to NFPA 92 and NFPA 101. If we see the paragraph on the left side of the screen, paragraph 4.4.2.2, which states the pressure difference across the door. In this paragraph, it is stated that the pressure difference across doors shall not cause the maximum force permitted to begin opening the door to be exceeded to the value stipulated in NFPA 101 or in the local codes and regulations. In the table stipulated in NFPA 101 can be found on the right side of the screen. This table is table A.4.4.2.2 and it is titled as the maximum pressure difference across doors. This table consists of two main sections. The first section, which is the first column on the left, which is the door closer force in pound of force, and the second section, which is the door width in inch and the correspondent related maximum pressurization value in inch water gauge. We can see, for example, for the first row of this table that in order to achieve a 6 pound of force at the horizontal, if we walk horizontally to the 32 inch or the 36 inch, we can find that the maximum pressurization at these given door values is vary between 0.45 up to 0.4 from pressurization difference. So this table, simply by knowing the door width and the door closer force, you can get the maximum allowable pressure difference. Okay, but how do I calculate the door closer force, which is the first column? To calculate this, you need to read the notes of this table, and afterwards we will go to the equation on the left side of the screen. The notes of this table says that the total opening force for the door is 30 pound of force, or the equivalent of 132 Newton. And the second note is that door height is 7 feet. The third note is that the distance from the doorknob to the knob side of the door is 3 inch. So now I have the maximum total opening door force, which is 30 pound of force. I will use it in the equation on the left side of the screen as F, or the term F, and I will use it in the equation of F equals FR plus 5.2 multiplied by W multiplied by A multiplied by delta V divided over 2 multiplied by W minus D. So what is this equation? This equation helps you estimate the opening force to overcome the door closer, which is the door closer force, which we saw in table on the right side of the screen. So what are the inputs that I can use to enter this equation? First of all, before understanding the inputs, you need to look at the figure on the bottom right side of the screen. This figure gives you the width of the door, the force direction, and the force location, and it gives you the distance between the knob of the door and the door opening. So these are the inputs that you are going to use in the equation, along with the inputs from the table above. So back to the equation, we can see that F equals Fr plus these terms. So F, I already have it as an input because F is the maximum operating force allowable to be on a door, which is 30 pound of force or 132 Newton. So this is already a given, F. But Fr is not a given. I need to calculate Fr to go with it to the door closer force. And I have an input of W, which is the width of the door, and delta B, which is the pressure difference across the door, and I have D, which is distance from the doorknob to the knob side of the door. So you can use this equation as a checkup at the end of the calculation to cross-check that your value is not exceeding the maximum allowable value in this table. And here are some recommendations from other building codes. If we refer to the paragraph on the right side of the screen, and this is quoted from the IBC or the International Building Code, Chapter 9, Section 909, you can see that the pressurization method, this paragraph, I'm reading the paragraph now. Pressurization method. The primary mechanical means of controlling smoke shall be by pressure difference across smoke barrier. Maintaining of a tenable environment is not required in the smoke control zone of a fire origin. And I'm going to follow to paragraph 909.6.1, which is the minimum pressure difference. The pressure difference across a smoke barrier used to separate smoke zones shall not be less than 0.05 inch water gauge in fully sprinklered buildings. In buildings permitted to be other than fully sprinklered, the smoke control system shall be designed to achieve a pressure difference not less than 2 times the maximum calculated pressure difference produced by the design fire. In paragraph 909.6.2, which is titled the maximum pressure difference, it is mentioned that the maximum air pressure difference across a smoke barrier shall be determined by the required door opening or door closing force. The actual force required to open the exit door when the system is in the smoke control mode shall be in accordance with section 1010.1.3. Opening and closing forces for other doors shall be determined by standard engineering. Following up to section 101.1.3, which is titled as door opening forces. The force for pushing or pulling open interior swinging egress doors other than fire doors shall not exceed 5 pounds or 22 Newton. These forces do not apply to the force required to retract the latch bolts or the disengage other devices that hold the door in closed position. For other swinging doors as well as sliding doors, the door latch shall release when subjected to a 15 pound or 67 Newton of force. The door shall be set in motion when subjected to a 30 pound of force or 133 Newton of force. So basically these are the requirements of the International Building Code. However, if you refer to the paragraph on the left side of the screen, this is an example of the local building code of Saudi Arabia, and this is largely quoted from the International Code Council. We can see on the paragraph 909.20.4.4, which is titled as Stairway or Ramp Shaft Air Movement System. It's highlighted in yellow what I'm going to read now, which is the stairway or ramp shaft shall be provided with a dampered relief opening and supplied with sufficient air to maintain a minimum positive pressure of 25 Pascal of water in the shaft relative to the vestibule of all doors closed. And I'm going to go to the section below, which is section 909.20.5, which is the stairway and ramp pressurization alternative. When the building is equipped throughout with automatic sprinkler system in accordance with section 903.3.1.1, the vestibule is not required, provided that each interior exit, stairway or ramp is pressurized not less than 25 Pascal of water and not more than 87 Pascal of water. in the shaft relative to the building. So this is an example of the local code requirement, which is stating a clear and specified value for the pressurization. Let us discuss a phenomena we explained earlier in the course, which is the stack effect on the staircase pressurization. If we look at the three figures on the right side of the screen, we can see an illustration of the smoke movement in a high-rise building due to the normal stack effect. In figures A, B, and C, we can see a fire is happening in different locations with respect to the neutral plane of the building, and we are assuming that the neutral plane is in the middle of the building. So in figure A, in case of a fire that happened below the neutral plane, and we are going to assume that the fire have enough buoyancy force to overcome the stack effect, and it will move upward through the shaft, the vertical shaft in the middle of the building, which is, for example, the elevator shaft or the staircase enclosure. And as we know that the air movement pattern in the normal stack effect is that the air and smoke will move upward from bottom to top. That's why the smoke will spread quickly through the vertical shaft from bottom to top. And after this, it will start to spread horizontally on the top floors. That's why we can see that the top floors are having smoke accumulation, although there is no fire happening on the top floors in figure A. And this is the danger of the stack effect. And that's why it's very important when designing a pressurization of a vertical enclosure like the staircase to allow a degree of safety to overcome the buoyancy effect of the hot smoke and the stack effect as well. Let's go to figure B. In figure B, we can see a fire is happening in the top floors, which is located above the neutral plane, but the fire does not have sufficient buoyancy to overcome the stack effect. That's why it's not spreading. And this is the correct situation in the pressurization, which is in figure B. However, if you refer to figure C, you can see the fire above the neutral plane, but the smoke is spreading through the shaft because the buoyancy effect of the fire have overcome the stack effect and spread vertically in the shaft, and from the shaft it's spreading horizontally on the floors above the fire, although these floors does not have any fire. So let us debunk some of the myths which are commonly said and handled when it comes to the stack effect on the staircase pressurization. The first myth is that the pressure difference due to stack effect is nearly proportional to the temperature difference between the building and the outside. And the correction of this myth or the fact is that this pressure difference is nearly proportional to the temperature difference between a shaft enclosure, the vertical shaft enclosure, and the outside of the building. The second myth is that it is a myth that stack effect is the major factor impacting the stairwell and elevator pressurization. However, this is not correct and not accurate, because the fact of this is that today the impact of the stack effect is minor factor for most pressurized stairwell and elevators. Why? Because the pressurization air for many stairwells and elevators is untreated outside air that is not heated or cooled. That's why the temperature of these shafts is often nearly the same as the outside temperature, and the impact of the stack effect is significantly reduced as compared to shaft pressurization with air treated to the building temperature. The first thing you need to know and understand in order to be able to calculate the pressurization flow rate required is the leakage area. So what is the leakage area? As we all know, there are leakage areas and leakage gaps around the doors and in the form of cracks in the wall that is commonly shared between the pressurized enclosure and the non-pressurized enclosure. So these leakage area exfiltrate air, which means that air, once you supply air into the stair that you need to pressurize, the part of the air will escape from these gaps under the doors and these cracks in the walls. So what you need to understand is that the first thing you need to determine is the cracks area and the leakage area. After you determine the cracks area and the leakage area, you will use it in the orifice equation, which is on the top right side of the screen. And also I'm going to assume that you as a designer will know the specific amount of pressurization which you need to apply. So now you have two inputs and one output of the equation. You have the A and you have the delta B. You can easily decide and calculate the infiltration airflow in CFM. You can see the orifice equation equals Q and Q equals 2610 multiplied by A multiplied by the square root of delta V. And me as a designer, I know the limitations and I've chosen a pressurization value. For example, it will be 0.2 inch water gauge. And I know the area of the leakage because I know the amount of doors and the number of doors, and I know the area of the concrete walls, so I can calculate the gaps. Once I calculate the gaps and I have the pressure difference, I will use them in this equation to calculate easily the infiltration airflow. This infiltration airflow is the flow that is required to maintain a pressure, given that there are these leakage areas inside the place. Okay, so how do I calculate the leakage area? If you refer to table A.4.4.4.3, which is titled as typical leakage area for walls and floors of commercial building, you can find here tabulated values for the leakage area, where you can find this table consisting of three main columns. The first column, which is a construction element, you need to calculate the leakage from. The second column, which is the tightness. Is it tight, is it average, or is it loose? And the third column, which is the area ratio. And area ratio is the area of the gaps divided over the area of the wall, or the area of the gaps divided over the area of the door. And there is a note below this table that is explaining the area ratio. It is stating that for a wall, the area ratio is the area of the leakage through the wall divided by the total wall area. For a floor, it is the area ratio for the area of the leakage through the floor divided by the total area of the floor. So you can see that this table have four main rows. The first row is for the exterior building walls, including construction cracks and cracks around windows and doors, and with emphasis to the exterior building walls. And the second column, which is the staircase walls, including construction cracks but not cracks around the windows and doors. The third row, which is the elevator shaft wall, and the fourth row, which is for the floors. So when you do a pressurization calculation, you will calculate the leakage area simply by defining the walls surrounding the enclosure of the staircase, and are these walls external or internal, and then you will use this table to calculate the area ratio, and you will multiply the area ratio by the area of the entire walls. So now we have understood the leakage area from the floors and the walls of the space you need to pressurize. What about the leakage area from the doors? Of course, you need to calculate the leakage area from everything inside the staircase enclosure, including the doors when they are open and including the doors when they are closed. But how do I calculate the leakage area from the closed door? You can calculate the leakage area from the closed door by knowing the gap in millimeters between the door frame and the opening or the cut of the door. Which means that if you look at any door, you will find a specific gap between the wooden door and the concrete. This gap ranges usually between 2 to 4 millimeters, and by knowing this gap, you can multiply it by the perimeter of the door. And we are going to assume that this door, for example, is 2.2 meter high and 90 centimeter wide. So in order to estimate the leakage area from the door gaps when the doors are closed, you will simply assume that the perimeter of the door is 2.2 plus 0.9 plus 2.2 plus 0.9 and multiply it in the thickness of the gap. Let's assume that this is 3 millimeters. Once you multiply the perimeter of the door in the gap thickness, you will get the leakage area from when the doors are closed. So you will sum it as an algebraic sum to calculate the total leakage area from the total number of doors. For example, if your staircase have 10 doors, then you will multiply the leakage area by 10, so that you can get the leakage area from the entire 10 doors when they are closed. After this, you will calculate the leakage area from the door when it is open. And this can be done easily using the continuity equation. Continuity equation is saying that Q, which is the flow rate, equals the A, which is the area, multiplied by the velocity. The A of the door, which is the 2.2 multiplied by 0.9, or the width and the height of the door. And the V, which is the velocity, and the velocity is usually considered as 1 meter per second in accordance with ASHRAE and the international codes. This velocity ensures that the smoke will not enter the space that you need to pressurize, However, it also ensures that there will not be any negative circulation of air and smoke. If the velocity is too high, it will create circulations and it might lead to adverse effects of smoke infiltration from these circulations. So you can get the flow rate accordingly from the open and closed doors and from the walls and floors. Now you can sum this flow and multiply it by a factor of safety to get the pressurization that you need for the staircase. But this is a simple scenario. What if I have multiple doors? What if I have the multiple doors arranged in series or in parallel that are connected to the pressurized space? Well, in this case, you need to understand the effect of air leakage path through the open doors if they are in parallel or if they are in series. If you refer to the figure on the left side of the screen, you can see that in the event of having doors or leakage paths arranged in series, which means that door is delivering to door, is delivering to door, door after door in series. They're not in parallel. They're not more than one door. It's only one door at a time. In this case, you can say that the doors or the leakage path will be in series. In this scenario, you will calculate the leakage area from the entire doors, and you will get the inverse of this and sum it as follows, as highlighted below in the equation of the effective area. So this is the effective leakage path area equation, which you can see on the bottom side of the screen. However, if you are having a pressurized space that is opening into more than one enclosure or more than one door, or in this case you will have doors open in parallel, your pressurization door will open to more than one door. So in this case it is a leakage path in parallel. In this case you will sum it as an algebraic sum, as shown in the effective area equation on the bottom right side of the screen. So now we have reached the end of this part at which we are going to solve an example together. But before solving the example, let us summarize the steps that are required for the staircase pressurization system sizing. The first step is the flow calculation of the fan capacity, and the second step is the fan external static pressure drop calculation, and the third step, which is the sizing of the accessories like the relief damper and the air outlets and the duct. As for the first step, which is the flow calculation, first of all, the first step you would want to do is to estimate and calculate the fan sizing. And by fan sizing, I mean the flow capacity. So in order to determine the flow required for pressurization, as we said, we need the pressurization fan to overcome the leakage from all cracks and gaps in the staircase enclosure. And this is in order to sustain a specific amount of pressurization. So in general, we are going to use the orifice equation to specify the flow required for infiltration or the flow required for pressurization that will overcome the leaks from the gaps in the entire enclosure of the staircase, and this is to maintain a specific pressure range. So first of all, I need step number 1, I will choose the pressurization range or the pressurization value or the delta B or the pressure drop value. I'm going to consider a value of 35 up to 50 Pascal or 0.14 up to 0.2 inch water gauge. And the second step is that I will calculate the flow through the cracks of the walls and slab of the staircase or the shaft enclosure using the orifice equation. And this can be done from the tables of the cracks, and I will use it giving the step number 1 to obtain the flow that will exfiltrate or infiltrate from these gaps or cracks. Step number 3 is to calculate the flow in order to maintain the specified or required pressure drop through the closed door gaps using the orifice equation. As we said before, we know the gaps area, and using this area and using the pressurization value, you can get the required flow that will exfiltrate from these gaps. Step number 4, which is to calculate the flow to maintain the pressure through some open doors using the continuity equation. After this, I'm going to sum all of the flows I have calculated, which are flow with reference Q1, which is the flow through the cracks of the walls, and flow with reference Q2, which is the flow through the gaps of the door frames for the doors that are closed. And I'm going to sum also Q3, which is the flow through the open doors that will be opened during a fire scenario. I'm going to multiply it in a factor of safety, and here I am having the total required flow rate of the fan. After this, I will do the cross-checking to make sure that the forces on the doors are not excessive, and to make sure that the stack effect and the buoyancy effect are not causing me any problems or loss of pressurization. After this, I'm going to step number 2, which is the ESP calculation of the fan, and this means that I need to calculate all the pressure drops in the ducts and in the dampers and in the grills or accessories, and I will have to also consider the stack effect, and I will multiply it in a factor of safety. After this, I'm going to size the grills and the dampers based on the continuity equation, which states that the Q, or the flow rate, equals the area multiplied by the velocity. I have the velocity of the air outlets and the damper, and I have the flow rate, so I can easily calculate the required area, and then I will enter any catalog and select the sizing from the catalog based on this effective area. In this video, we are going to discuss the subject of the zoned smoke control system. Zone smoke control systems, or what's known as the pressure sandwich system, is simply said you create a pressure sandwich. By pressure sandwich, this means that if the detectors detected a fire in a floor, then this floor will be on the exhaust mode, and the floor on top of it and below it will be either on the exhaust mode as well, or will be either positive pressurization mode. This will mean that you will be able to contain the smoke from spreading in the remaining of the floors. And we can see this on the figure on the right side of the screen. You can see two scenarios. These scenarios are expressing the interaction between the zone smoke control and the pressurization of the stairwell. You can see two scenarios. The scenario on the top, which is to create a positive and negative pressure sandwich. In this scenario, you can see the smoke zone in the middle, which have a gray shading, and this gray shading is representing the smoke spread. So in this case, in the scenario of a fire, this active fire floor will be turned on to be exhausting smoke away from the floor, while the floor above and below will be pressurized positively in order to prevent any smoke infiltration above or below. So this is what's called as a pressure sandwich. While the scenario on the bottom will mean that when a fire is detected in the exhausted floor or in the floor in the middle, which is shaded in gray, both the active fire floor and the floor above and below will be exhausted to extract any smoke from this area. Not only the fire area, but one floor above, one floor below. But there is a note on the bottom right side of screen that is saying, because of the potential for negative stairwell pressurization, zone smoke control using both exhaust and pressurization is not recommended for tall buildings, except as shown here. And also the second note is that the zone smoke control using only exhaust does not have the potential for negative stairwell pressurization that exists with the zone smoke control using both exhaust and pressurization. So what does this mean? This means that if you applied a negative pressure on the floor having the fire and a positive pressure above and below, this positive pressure may counteract or may cancel the pressurization of the staircase enclosure, because as we know, if we pressurize the staircase, there will be infiltration of the air from the gaps of the door at this floor. But if you supplied a pressurization value on inside the floor that counteracts the pressurization coming from the stairs, then this means that you will cancel the pressurization of this staircase floor. And if the pressurized value used for this floor is more than the pressurization of the staircase, you will create a negative pressure in the staircase at this local point. So if any smoke has spread in this floor, this smoke will infiltrate into the staircase due to the negative pressure exerted by the floor onto the staircase. That's why it's very tricky and it's not recommended to be used, because it's a complicated strategy that sometimes have adverse effects. You need also to know that the smoke zone can be a single or more than a single floor, meaning that it can be a single or multiple floors. But in these scenarios, if you are using a zone smoke control system, then it is highly recommended to conduct a ZFD analysis to validate that this scenario will perform as behaved and this scenario will not create any negative pressure on the staircase. Here are some notes that you need to pay attention to when designing a zone smoke control system. Zone smoke control system require a great deal of attention, because sometimes and in many scenarios it can have adverse effects. That's why you will find it not recommended in many scenarios. So the zone smoke control system can be applied or done using three common methods. The first method, which is to use exterior wall venting. and the second method, which is to use smoke shaft, and the third method, which is to use mechanical exhaust. Exterior wall venting concept will mean that you will put a relief vent or a vent that will open automatically in the event of a fire mode to vent out the smoke directly outside the building. So this means that the wall you will put the vent on, it has to be an exterior wall. It cannot be internal wall inside the building. But this option will mean that the smoke will directly exit the building. So if there is any opening like balcony or any opening on the floors above this floor, it might have a potential threat that smoke will come right up in these balconies. Option number 2, which is the smoke shaft. Smoke shaft is simply the same like option number 1, but instead of discharging outside the building, you will discharge in a smoke shaft. And this smoke shaft utilizes the stack effect, and it's usually applied on the large open floor area. For example, if I have an open floor for a factory or an office building, and this open floor have a relatively large horizontal area with no partitions or separations or walls, this might be subject to applicable application of the smoke shaft concept. Smoke shaft concept is simply you are creating a shaft to catch the smoke at high level. Due to the buoyancy and the stacked effect of the smoke, it will rise up to the high levels, so you can catch it very easily. And option number 3, which is using the mechanical extract fans to extract the smoke from the space being subjected to a zoned smoke control system, and the recommended number of air change per hour is 6. On the figure on the top right side of the screen, we can see the application of the zoned smoke control. We can see that the floor in the middle is having a fire, and the fire is being extracted from this floor directly to outside the building, because this pressure will be under negative pressure due to the extract nature. However, the floor above and the floor below will have a positive pressure to prevent any infiltration of smoke. You need also to pay attention to the activation signals for the pressurization of the zoned smoke control system. For this, we need to refer to the table on the bottom right side of the screen, which is table 50.1, which is obtained from SFPA. This table represents the activation signal sources and if they are applicable or not. We can see that this table have 5 columns. The first column, which is describing the system or the type of the pressurization or the smoke containment system. Second column is representing the smoke detector, if it's applicable to be activated via the smoke detector or no. Third column is the heat detector. Fourth column is the sprinkler water flow. And last column is the manual pull station. We can see in the rows that the first row is the stairwell pressurization. Stairwell pressurization can be activated by a signal from the smoke detector or from the heat detector or from the sprinkler water flow or from the manual pull station. Elevator pressurization can be detected also from all these 4 items. However, the zoned smoke control can be detected only from the smoke detector or from the heat detector or from the sprinkler water flow, but it cannot be detected or activated based on the manual pull station signal, because this poses a danger of activating the wrong floor, because the manual pull station is activated by the occupants, and maybe one or more of the occupants will use the manual pull station at the wrong floor, which means that you will create the wrong pressure sandwich, and this can have extremely adverse effect if it was an available option to the occupants. That's why it's very important to understand that the manual pull station activation option or activation signal is not and should not be used for the zoned smoke control. And this is also mentioned on the note below the table, saying manual pull station are not recommended for activation of stairwell elevator pressurization system that rely on the fire floor exhaust or the zoned smoke control concept. You need also to note, as a designer, you should be very careful when evaluating the control interface between the HVAC equipment during the smoke or the fire mode if you are going to use or utilize the HVAC equipment ducting or fans. This can be illustrated from the figure on the bottom left side of the screen, where you can see that the air handling unit is illustrated with the duct of the supply and the duct of the return and a bypass damper having a closed damper. So the return fan is responsible for pushing the air through the return duct until it reaches the air conditioning equipment filter or coil. And the supply fan is responsible for supplying the air through the distribution ductwork to the air outlets and air terminals. So in the case of a fire, what will happen is that the air handling unit should normally close the dampers which are penetrating the fire rated walls, and especially the dampers on the supply side, because I don't want to supply fresh oxygen to the fire. But if I am, as a designer, have decided to use the return duct as a smoke extract duct, then I should be very careful with this option, because in this case there should be a bypass damper that is connecting the return and the supply. This bypass damper should be closed automatically in the event of a fire, which can be seen on the return damper closed on the figure on the left side of the screen. But what if anything happened and this damper did not close? What will happen is that smoke will spread throughout the entire distribution network of the duct, and it will intentionally fill all the occupied zones that are connected to the same air handling unit. Not only the area that is having fire, but the entire zones and the entire spaces will be filled with smoke intentionally, and there will be no stopping for the spread of the smoke. That's why it's very risky and it's very dangerous to use the HVAC system with the recirculation capability in case of the smoke mode. If we refer to the figure on the bottom right side of the screen, we can see a caution that is quoted from ASHRAE regarding using this system, and it's mentioned that this system may not work and should not be used. And the notes for that are that: note number 1, this system is not recommended because it is generally not achieving a satisfactory pressure difference to control the smoke movement.